Speaker will be Mark Bernhofen from the University of Leeds. And Mark will present assessing the role of global data sets for flood risk management at national and catchment scales. We're very pleased to have actually Mark here live because he didn't feel very well. So I much appreciate that you're still giving your presentation. Go ahead, Mark.
Thank you, Albert. Can you see my screen?
Yes, I can.
All right, perfect. Good afternoon, everyone. My name is Mark Bernhofen. I'm a PhD student at the University of Leeds. And like Albert just mentioned, I'm just recovering from COVID over the weekend, but feeling good to give this presentation. So today I'm going to be talking about a project we've been working on called Assessing the Role of Global Data Sets for Flood Risk Management at National and Catchment Scales. And I'd like to start by acknowledging all the co-authors who've been working on this project with me, who are all listed on this slide. So this project is part of the larger Water Security and Sustainable Development Hub, which connects a number of different organizations and academic institutions in 5 different countries to tackle challenges related to water. And these are the 5 countries which form the Water Hub: Colombia, England, Ethiopia, India, and Malaysia. And it's in these 5 countries where we'll be exploring the use of global data sets for flood risk management at national scales. So just to give you a bit of an overview of the project, there's been quite a lot of work dedicated to producing these global data sets over the last 2 decades. And they've been used in a number of high impact studies of global flood risk. And they've gotten to a point where some of them are detailed enough that they can be useful not just at the global scale, but at the national scale too. But there are a lot of global data sets out there, and they aren't all created equally. So while some may be useful at the national scale, others may not be. So our goal is to test all the global flood risk data sets that we can find for use at the national scale. And the Water Hub project gives us the opportunity to carry out a multi-country analysis and work collaboratively with water experts in each of the 5 countries to evaluate these data sets. So to evaluate the data, we're taking 2 approaches. The first approach, which I'll be presenting about today, is to carry out national flood risk assessments in each of the 5 countries using the global data and looking at where the data sets agree, where they disagree, and what sort of implications this has for national flood risk estimates. And the second approach, which I won't be presenting on today, but which I think is worth mentioning and is being led by colleagues at the School of Politics and International Studies here in Leeds, is to look at what capacity there is to use this data, considering the flood risk management structure and also the capabilities of regional and local governance within each country, while also exploring what local flood risk data already exists and how the global data could complement it. And that's being done through in-person interviews with water experts and professionals in each country. So now to take you through my part of the analysis, what global data are we using? So we're using data sets that fall under the 3 components of risk. So hazard, exposure, and vulnerability. And our criteria for choosing the data sets is that they have to have been used in previous studies of global flood risk. And they also need to be easily obtainable by the end user. So either they're freely available to download online, or the developer is happy to share their outputs with potential users. So to represent hazard, we use 5 different global flood models. We consider only fluvial undefended flooding. So these models output maximum flood extents and depths for varying return period floods. And we use only the 100-year return period flood from each model. So on the center of the slide here, you can see the aggregated output of 6 different global flood models in Africa from a previous global flood partnership study, which was led by Mark Trigg. And in our study, we used the latest iteration of these global flood models. So these are the 5 global flood models which we're looking at in this study. From the exposure side of things, we use 7 different global population data sets to calculate exposure. So on the screen here, you can see how 4 of these 7 global population data sets compare over Nigeria. These data sets are all quite different. They use different approaches to distribute population. And the resolution of the data sets is also pretty different. So the most resolved has a resolution of around 30 meters, while the most coarse has a resolution of around 9 kilometers. And these are the population data sets we compare. So one thing that connects all these data sets is that they've been used to calculate flood exposure in a previous study of global flood risk. And finally, vulnerability. So I'd say that vulnerability is the component of risk that's been explored less at the global scale than both hazard and exposure. And that's why we use only 3 different approaches to calculating vulnerability. And these have been used in the study shown here on the slide. Each of these approaches uses some form of depth damage curve and a land use map to convert flood depth into economic damages. So we're looking only at direct economic damages. And these are the 3 approaches listed here. We named them after the land cover map that's used within each approach. But I'll explain a bit more about that later in the presentation. So to begin taking you through some of our results, looking first at the agreement between the data sets. So to calculate agreement between the global flood models, we take the flood extents from each of the models and we overlay them on one another to produce this aggregated map of model agreement, which you can see on the left for Colombia. So you can see that the green areas are where there's greater model agreement, and it goes down in agreement all the way down to the yellow areas where only one of the 5 models predicts flooding. So across the 5 countries, we found that generally the models agreed more on larger rivers, like you can see for the Magdalena River here to the north of Colombia. And the disagreement was higher on smaller rivers, as you can see for this yellow patch in central Colombia. And this is because the models all have different minimum threshold river sizes, which means that some of the models don't model flooding on small rivers. Another thing we found was that disagreement was higher in coastal basins than in inland basins. And this is likely due to the low elevation relief in coastal basins, making flood modeling more difficult. And also we found that there were some differences between the coastal boundary conditions between the models. So now looking at global population agreement, this was done much in the same way that we calculated model agreement, but I should emphasize that in the agreement calculation, we aren't looking at differences in population density, just at populated area. So it sort of limits the conclusions and observations we can make. The first thing we found was that the differences in resolution between the population data sets were really significant. So the finest data set at 30 meters resolution can basically pick out individual buildings, while the coarsest data set at 9 kilometers resolution is only really able to identify major cities. We also found that urban areas saw greater agreement than rural areas. And this is largely due to the different approaches that the data sets take to mapping rural populations. So the data sets can be either constrained or unconstrained. Constrained population data sets distribute census data only over identified settlements, while unconstrained population data sets spread some residual census data over an uninhabited area under the assumption that not all rural settlements can be identified from satellite imagery globally. And that's why you have these large patches of dark purple in Southeast Colombia. So what about when we combine these data sets to calculate flood exposure? So to calculate exposure, we intersect the global flood maps with the global population data sets. And this figure on the right is from the paper we're writing, showing the flood exposure calculated in each of the 5 countries. So each column here is a different global flood model. The dots in each column are a national flood exposure estimate calculated using a global population data set. The red line is the mean national flood exposure estimate for each global flood model. And these lines in the right-hand column are the average exposure calculated with each of the global population data sets. So I'll just take you through some of our key findings. Firstly, we found that global flood model river representation had a significant impact on national flood exposure estimates. And this can be seen in Colombia, where Fathom predicts twice as much exposure as the rest of the models. And this is because it models flooding on more rivers than the rest. Similarly, in Ethiopia, there are a few major cities, such as the capital Addis Ababa, where the rivers that flow through the city are only modeled by one of the global flood models, and that was Fathom again, which is why there are such large differences in national flood exposure in Ethiopia. Another thing we found was that in countries with large coast-to-area ratios, such as England and Malaysia, the GLOFRIS model predicted a lot more exposure. And this was because of the 5 models, it was the one that consistently predicted more inundation in coastal basins relative to the rest. We also found that in a number of countries, small towns were missed by some of the population data sets completely. And while this didn't have a huge effect on national flood exposure estimates, when we started looking at flood exposure estimates at the basin level, this was quite significant. And now looking at some trends that we observed across the 5 countries, or trends that we didn't observe, well, we found that no data set consistently predicted the most or least exposure, which meant that the results were highly country and basin specific. But we did find that the choice of global flood model had a greater impact on exposure estimates than the choice of population data. And here we do a little cross-country comparison of normalized flood exposure. So you can see the spread of the different national flood exposure estimates in each of the 5 countries, and the spread of the national flood exposure estimates in India and Malaysia is quite large compared with England and Ethiopia. And in Colombia, the spread of exposure estimates is relatively low when the Fathom data isn't considered. But when the Fathom data is considered, the spread is quite high. And finally, moving on to vulnerability or flood damages. So the results for the national flood damages are shown on this slide. So this is another figure from the paper we're writing. Like I mentioned earlier, we use 3 different vulnerability approaches, globe cover, GHSL, and HIDE. And each of these approaches is named after the land cover map that's used in their calculations. So in this figure, each of these columns is a global flood model, and each of the bars within the column is the national flood damages calculated using one of the vulnerability methods. So the globe cover approach, which is the far left bar in each column, splits damages into 5 different sectors. So residential, industrial, infrastructure, commercial, and agriculture. The GHSL approach, which is the central bar in each column, splits damages into 3 different sectors, so residential, industrial, and commercial. And the HIDE approach just calculates urban damages. So that's the far right bar in each column. So the top row of results show national damages normalized respective to national GDP in each country. And the bottom row shows total national damages. So you can see in Ethiopia that flood damages are comparatively small to the other 4 countries, and that's why this yellow inset is on a different scale to the other parts of the chart. So our main finding from the vulnerability analysis is that the choice of vulnerability approach has a far larger impact on national flood damage estimates than the choice of global flood model. And this is largely due to a number of uncertainties within the vulnerability calculation. And I'll take you through the 2 main uncertainties we found now. So the first uncertainty comes from the land cover map used. So the majority of national damages come from urban damages, although the globe cover approach does include some agricultural damages. So these are the 3 land cover maps we use in our calculation, and you can see them for Colombia here. And you can see that the urban area defined by the 3 maps is really different. So globe cover's urban area is 99 kilometers squared, GHSL urban area is 946 kilometers squared, and the HIDE urban area is 2,436 kilometers squared. So if we go back and look at the damage results, you can see that the differences in urban area are reflected directly in the differences in damages in Colombia. So you've got the HIDE damages, which had the largest urban area, is a lot larger than the globe cover damages, which had the smallest urban area and a bit more than double the GHSL damages, which was somewhere in the middle in terms of urban area. And this is something that we found reflected in the direct damages across the different countries. The second uncertainty, which doesn't have as large an effect on national flood damages as the land cover map used, but still represents a significant uncertainty, in these global approaches is the urban split. So currently, global land cover maps don't distinguish between the different types of urban land use. They just define urban areas as one uniform area. Because of that, these approaches, which calculate urban damages per sector, use constant global ratios of urban split. And here you can see the ratios used by two of the approaches in this study. And while this doesn't have a huge effect on total national flood damages, if you're looking at damages at the city level and at the sector level, the differences in damages can be quite significant. All right, so I've given you a bit of a glimpse into some of the key results from our study, and I'll just summarize some of our main conclusions. So firstly, we found that national flood risk estimates using different global data sets vary significantly. And we found that the data sets differ enough that they can't really be used interchangeably without understanding the differences between them and the limitations of certain data. And I'd certainly say that they are data sets that aren't appropriate for use at the national scale. Secondly, the results are very country and basin dependent. So while one model or data set may predict a lot more exposure or damage in one country, it doesn't mean that it will do the same in another country. And finally, while some of the hazard and population data is now detailed enough to be relevant at these scales, I guess we recommend caution when using the different vulnerability approaches, as they're rife with lots of different assumptions and uncertainties. However, these vulnerability approaches are able to ingest more detailed national data where available. So for example, if there are more detailed national land use maps available, it would definitely improve the vulnerability calculation. All right, and that brings me to the end. Thank you for listening. And just a quick plug before I finish, I'm due to finish my PhD in December. So if you have a postdoc or a job that you think I should apply to, please don't hesitate to email me.